Okay, welcome. This video is the supplement to the lecture on standing waves. This is a video available in the supplementary materials that gives a overview of the demo that we did in class to first just kind of show you and help you visualize what a standing wave is.
Standing waves are a result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. Sending the pulse at twice the frequency results in the second harmonic. If I triple the frequency, I get the third harmonic.
Okay, so that gives you an idea of the overall shape of a standing wave. And we're done with him. So that gives us an idea of how they're formed. And they're formed really by two transverse waves that pass through each other. That's what you saw with the reflection there. This animation shows you the idea. We have a red wave, which is a traveling wave moving to the right, and a blue wave that's a traveling wave moving to the left. As they pass through, the displacements of the two waves add together. This is called superposition, and this is something that we're going to study in a lot of detail later in the course. For now, just try and see how when the peaks line up, you get a very tall wave like right there, and when the peaks line up with the troughs, you get almost zero displacement. So we get different combinations as waves move through each other, and the black wave is the combination of the two, which you notice doesn't really look like it moves anywhere, giving it the name the standing wave. So here we have an image of, again, what a standing wave looks like. Notice the wavelength on the diagram here. It's between two of these dots, these red dots, which you can see don't move at all. There are points on a standing wave that don't move. We call these nodes. They don't oscillate, they have zero amplitude. We can label them all with ends like this, and the points in between that have the maximum oscillation or maximum amplitude, we call antinodes. And so you can see the antinodes fit in between the nodes. There are points in between the antinodes and the nodes that oscillate just a little bit. So it turns out all the particles have different amplitudes. This is not the case for a traveling wave where all particles have the same amplitude. Another key difference is that a standing wave, because the shape of the wave doesn't really move, it doesn't transfer energy from one end to the other in the same way that a traveling wave does. We do say that the standing wave has energy because obviously there's motion, so there's some energy kind of tied up in the wave, but it's not being sent from one end to the other like it is in a traveling wave. This table details some of the important differences between a traveling wave and a standing wave. You do want to memorize these and be able to compare them. Notice the last point here talks about the particles in a loop being in phase. All the points, say, between these two nodes move up and down together. Again, that's not the same for a traveling wave where adjacent particles are a little bit out of phase. In a standing wave, the particles are either totally in phase or totally out of phase. For example, these particles at this antinode are completely out of phase with these particles. While one moves up, the other moves down, and vice versa. This gives us our first practical example of a standing wave, which would be a wave on a string. This represents a wave on a string fixed at both ends. This a good common example is any instrument, any stringed instrument like a piano or a guitar, or just your slinky or a string. In order for it to be a standing wave on a string fixed at both ends, the two ends must be nodes. So for all of these waves, we're going to talk about boundary conditions, what has to be true at either end. And for this to be a fixed string, obviously these points can't move up and down. So by definition, they have to be nodes. which means there's only a certain set of frequencies or wavelengths that can fit on the standing wave given those boundary conditions. The different kind of possibilities that exist we call the harmonics. And the first harmonic we define as a wave with the shortest possible frequency or the longest possible wavelength that can match the conditions. Later harmonics will define based on the first harmonic. Here's an example for the string fixed at both ends. This is the first example we saw in that video, where this is the simplest standing wave you can form. 2 nodes on either end and an antinode in between. Okay, because we need the 2 nodes at either end, you always need an antinode in between adjacent nodes, so this is the simplest wave that will possibly fit. We call this the first harmonic. As you saw in the demo then, the second harmonic would be defined as double the frequency of the first harmonic. And when we doubled the frequency, we saw a shape that looked like this. And it's essentially the next most complicated shape you can fit. Instead of just 2 nodes, we have 1, 2, 3 nodes with the antinodes in between each of them. Finally, if you were to triple the frequency that you used to make the first harmonic, we saw you get this shape, and notice the pattern. There's 1, 2, 3, 4 nodes on the third harmonic. So now we'll look at the math of the first harmonic on a string. This picture gives you a good visualization of what that shape looks like. Again, this is the simplest standing wave that we can form on a string, fixed at both ends. What you want to see is that this shape is half of one wavelength. One full wavelength here is represented by the dotted line. You can see this is a full sine wave, or really a negative sine wave. At this moment in time is what we see. And that's what you have to do to start the derivation of this equation, is realize that the length of the string is half of the longest wavelength we can fit. So L we're going to say is lambda the wavelength divided by 2. We can solve for wavelength and use the wave equation to substitute in and find the wave speed. So if the wavelength is 2L and the speed is frequency times wavelength, then the speed should be 2 times frequency times length of the string. Solving for frequency, we get this equation. Since this is a frequency of the first harmonic, we'll define it as f sub naught, or f sub 0, for the fundamental frequency, which just means the frequency of the first harmonic. This will always be the fundamental frequency for the first harmonic of a string fixed at both ends. And your options here are to understand this derivation, be able to make this sketch and realize that you have half of the simplest wavelength, use your wave equation and find the frequency that way, or memorize this equation. This is always the frequency of a string fixed at both ends, the fundamental frequency. One interesting consequence of this that you can think about is in designing instruments, the fundamental frequency is inversely related to the length, as in L is in the denominator here. So long length means a small frequency. This is why if you ever open up a piano or something like this, you'll notice that the low notes have the longest strings. The frequency in music is what you think of as the pitch. So a high frequency corresponds to a high pitch or a high sounding note. A low frequency corresponds to a low pitch. So all other things being equal, a longer string will have a shorter frequency that it likes to vibrate at. There are other factors that go in that affect the wave speed, like the tension that you tune the strings to and the linear density, but the length is a big factor. Now we'll look at some of the other harmonics on a string. The next most complicated shape that we could fit would have 2 nodes at the boundaries, because that's our condition, 2 nodes at the fixed ends of the string. Rather than node, antinode, node, we're going to stick 1 more node in between. As we saw earlier, we're going to call this the second harmonic, and we'll look at the math to see why. Here we do have 1 full wave that fits in between the ends perfectly. So the length of the string in this case is equal to 1 full wavelength. What this means is, since wave speed is frequency times wavelength, we're just going to substitute in L for lambda in our wave equation, solve for this frequency, and we get V over L. This is why this is called the second harmonic, because you'll notice that's double the fundamental frequency. If I multiply this by 2, I get this frequency, which is why we call this the second harmonic. Next, we'll look at the third harmonic. We see here we have 1.5 waves that fit in between the ends of the string. Since 1.5 waves fit, we'll say the length is 3/2 of a wavelength. We can solve for the wavelength as 2/3 of L, and we'll use our wave equation that wave speed is frequency times wavelength to get the frequency times the wavelength here. We take this and solve for F, and we find that it's 3V over 2L. And again, we find that this is 3 times our fundamental frequency. So we define it as a third harmonic. In general, then, the frequency of the nth harmonic is n times the fundamental frequency. This is for a string, and it should be noted that this equation is true for any frequency of a standing wave. This is how we define the nth harmonic. So you'd read this and write this as the frequency of the nth harmonic is equal to n times the fundamental frequency, where n is an integer number. For a string, any integer will work. That won't be true for all setups. Okay, here's a basic example using a guitar where we have the fundamental frequency and the length of the string. If we want to find the wave speed on the string, all we need to do is use the equation we came up with and the wave equation. Now, we have to mention that this equation is not in your data booklet. So again, you either have to memorize that this is the fundamental frequency for a wave on a string, or be able to go through the steps from 2 slides back and set that up. Once you know that, it's a very simple problem. You solve for V, we're going to plug in, don't forget to convert to meters, and we find 106 or so meters per second, which is true. That's about how fast a wave on a guitar string moves. Also remember a definition of the harmonics on a string. The second harmonic is defined as the wave with twice the fundamental frequency. So we just take their fundamental frequency of 82 Hertz and double it and get 164. Again, this works for any harmonic. The 107th harmonic would have a frequency of 107 times 82. Moving on, the other big type of wave that you will see in the standing wave problems is a wave in a pipe. And in fact, there are 2 types of pipes. We have 2 different types of boundaries that are possible in a pipe. So we have a couple boundary conditions to memorize. When we're talking about a pipe, we're talking about pressure waves or sound waves. We're talking about waves that move through the air longitudinally. These animations will help us visualize all of that. So here's a pipe that is, for example, closed at one end and open at the other end. You can see the blue represents the actual pipe. The rule should make sense if you think about it. At a closed end in a pipe, if we set up a sound wave, which is particles moving side to side, this must be a node, because if the particles were moving side to side at all, they would bust through the end of the pipe, which would be no good. So a closed end must be a node. The open end, because it's open to the air, the particles can have a maximum displacement here, and so this will actually be an antinode. Notice in this example there are a few nodes. There's a few spots where the particles don't seem to move at all. Right here looks to be a node. Right here looks to be another node. And above we have an animation that shows us how we usually graph this. This would be a displacement distance graph. And so notice we take the left-right motion of the particles and plot them vertically here. So we say moving to the left is negative, moving to the right is positive. And this lets us make a graph where we don't have two things right on top of each other. We have another type of pipe here that's open at both ends. And like we said, the boundary condition is that at any open end, you have an antinode, which means in this case, we would have an antinode at both ends, and it turns out here a node in between. So at either open end, the particles are free to move back and forth with maximum amplitude. Somewhere in between the two antinodes, there must be a node. You can never have two nodes next to each other. You can never have two antinodes next to each other. And here's just a couple other examples of the waves in a pipe. Just notice at all the closed ends there's a node. At all the open ends there's an antinode. So let's look at the open pipe in a little detail. We'll look at the first harmonic. Again, the simplest wave that will fit will be two antinodes at either end based on our boundary conditions. And since we need at least one node in between them, this is the simplest wave we can stick there. This would be a good diagram to have in your notes if you don't have it already, where you talk about the length of the pipe L, antinode on either end, a node here, and below we even draw what the particles are doing. So we can think about how these graphs represent the side-to-side motion of the particles. At the middle we have a node. We usually draw it like this, where there's no side-to-side motion, and the maximum side-to-side motion of the particles we represent with this kind of double wave. Up, say, means all the way to the right. Down, say, means all the way to the left. Here again, you should see that the length is half of a wavelength. The length L of the tube, we have half of, say, a cosine wave, or half of a negative cosine wave. So we saw for the wavelength, we get 2L, and it should be no big surprise if you look at the way the math works out. We get the same fundamental frequency for a pipe open at both ends as we did for a string fixed at both ends. It's essentially mirror image. The only difference is in a string we had two nodes with an antinode in between, which gave us half a wavelength. Here we have two antinodes with the node in between, but we still get half a wavelength. And since we're just using the wave equation, the math works out exactly the same. So the fundamental frequency for an open pipe is the same equation as the fundamental frequency for a string fixed at both ends. Just do realize that the V is different. One is the speed of the wave on the string. Here we have the speed of almost always the sound wave, unless we have some other type of longitudinal wave. But 99.9% of the time, this is the speed of sound, the speed of the longitudinal wave. L here is the length of the pipe, and the other equation is the length of the string. And just remember, the key difference is that here we're looking at a longitudinal wave. On the string, we're looking at a transverse wave. And so here we have antinodes on either end with a node in between. On the string, we had nodes on either end with an antinode in between. So it should follow that the math of all the harmonics works out exactly the same as well. And it does. And you can and should sketch these in your notes, the second and third harmonics for the open tube, and go ahead and work through the math and convince yourself that the fundamental frequency is the same, the frequency of the second harmonic is the same, of the third harmonic is the same, and so on. What that gives us is a general equation we can use for the frequency of the nth harmonic in relation to the speed and the length. It's going to be n times the speed divided by 2 times the length of the pipe. And here n is any integer, 1, 2, 3, they'll all work. So do make a note that this equation works as well for a wave on a string, because the math, again, works out exactly the same. All right, so far all the math is pretty straightforward, or at least pretty much all the same for an open pipe and for a string fixed at both ends. Again, you may want to work through this a few times to make sure you're comfortable making the sketches and deriving these frequency formulas, because you do not get them in the data booklet, or at least memorize your fundamental frequency equations. Better yet, memorize this. Last, we'll look at a closed pipe. These are weirder. They're different. because the boundary conditions are different. The boundary conditions tell us that the rule is at a closed end we need a node, and at an open end we need an antinode. This gives us our fundamental frequency of a very basic wave, because if I have a node and an antinode, I don't need to put anything in between. It's okay to have a node next to an antinode. What this gives me is actually a quarter of a wavelength. This is the first quarter of, say, a sine wave. To finish the wave, I would have to come all the way out like this. That's now half a cycle, and I would have to then go down again and come back up to 0. So do make sure you have a sketch and you can visualize why this is 1/4 of a wavelength, but the fundamental frequency for a closed pipe is 1/4 of a wavelength. What that means is, if we use our wave equation, first we're solving for the wavelength, lambda, which would be equal to 4 times L. So I'm going to do wave speed equals lambda times frequency. So 4L times the frequency gives me the speed of the wave. And now I solve for the frequency of the simplest wave, which I call the fundamental frequency, V over 4L. This is the fundamental frequency for a closed pipe. So again, you need to either be able to make the sketch and derive the equation, or memorize that this is the fundamental frequency of a closed pipe. What gets interesting is when we look at the next simplest wave, where again I have a node at the closed end, an antinode at the open end. What I need then to put more things in between is to add both another node and an antinode. Because again, you can't have two nodes next to each other, you can't have two antinodes next to each other. So I get the na-na wave, and you'll see that this is actually 3/4 of a wavelength. To finish the full cycle, I would need to come back up like this, go another 1/4 of a cycle. But what fits is a 3/4 wavelength. What that means is if I solve for wavelength, I would get 4L divided by 3. I stick that in my wave equation, and I do 4L over 3 for my wavelength times the frequency. I get something like this. If we then solve this for frequency, we see we get 3V divided by 4L. Do make sure you can work through that algebra and try and notice what we have is 3 times our fundamental frequency. By definition, then, this is the third harmonic because it's 3 times the fundamental frequency, which is how we define our harmonics. What that means is there is no second harmonic for a closed pipe. There's no way to fit a wave that, if you want, is double the frequency. Only a 3 times frequency will work because of the way we have a 1/4 wavelength and then jump to 3/4 of a wavelength. Based on the boundary conditions, it's not possible to have a second harmonic in this closed pipe. Then the next simplest, again, we have a node, antinode, and we can stick 2 nodes in between. What we get is a full wave plus an extra 1/4. So we get 1 1/4 wavelengths. In other words, 5/4 of a wavelength is equal to the length of the pipe. Meaning the wavelength would be 4 times the length divided by 5. We multiply that wavelength by the frequency and get this equation. We solve this equation for frequency, and you see a pattern start to begin where we now have 5 times the fundamental frequency, meaning this is our 5th harmonic. So just like there was no second harmonic, there's no 4th harmonic for a closed pipe. You could draw these all day, the pattern would continue. There are no even number harmonics in a closed pipe. It's not possible to have. The general equation for the frequency of the nth harmonic then would look like this. We do n times v divided by 4L, so the number of the harmonic times the wave speed, which is the speed of sound since we're looking at a longitudinal wave in air. We divide by 4 times the length of the pipe. And in this case, n can only be an odd numbered integer. 1, 3, 5, 7, so on. You can't use n equals 2 in this equation because the second harmonic is not possible. So again, this is an equation you can memorize, but you need to understand the background especially why there can't be a 2, a 4, a 6, and so on. The other thing to notice is this equation for both the other ones was NV over 2L. So the fundamental frequency of a closed pipe is half the fundamental frequency of an open pipe if all other things are the same. For example, this is why big pipe organs are closed at one end, because you make a much lower note with the same length pipe. And that's it. So again, use this video to go over especially the derivation of these equations, because you don't get them in the data booklet and you do need to be able to sketch these, think about your boundary conditions, and come up with the formulas for the frequencies.